Hello students. We're going to review Unit 7. So this is Unit 7 review video. We've got 4 standards on our Unit 7 Celebration of Knowledge. First one, 7A, students can connect exothermic and endothermic to phase changes in reaction diagrams. So things that are popping out there is exothermic, endothermic, you got to know what that is. You got to know your phase changes. And you got to know how to draw and understand reaction diagrams. Alright, 7b says students can use heating curves, latent heat, and specific heat capacity to describe the heating or cooling of substances. So you got to know what a heating curve looks like. Should be able to sketch one, especially if I give you a melting and boiling point. Got to understand why it plateaus, why it goes horizontal, that is. That's what a plateau is. You got to know what latent heat is and the equation that goes with it. Specific heat capacity, what it is, equation goes with it. And then 7c, students can do simple conversions. Alright, so this is things like kilojoules to joule, etc. We'll go in more detail later. And then the last standard, it's just literacy. So this is actually going to go into the grade book this time. I don't know how I can really review it in a video with you. It's just too much that goes into it. But all the TIEA paragraph writing that we've been doing for labs and things previously the entire year, reading skills, annotating, etc. All that stuff that is really, really important in life that we've got to make sure, as a school that you can do. Okay, so let's move on and do some review of these A, B, and C. Alright, whoops, sorry, wrong button. There we go. Alright, so first one is Unit 7A, oops, which has to do with exothermic, endothermic, phase changes, and reaction diagrams. Okay, so let's just start with exothermic and endothermic. Exothermic, endothermic. Hopefully you know the definitions here. Exothermic, we know that exo is like exit, right? So exothermic, it means heat leaves the system. Let me make this box a little bigger. Heat leaves the system. So that means delta H is negative. Products have less energy than reactants, and heat is a product because it's leaving the reactants. Alright, so endothermic means heat enters the system, so the opposite of everything I just wrote. So delta H is positive, and the products have more energy than reactants, which means heat is going in, so heat is a reactant. Okay, we also need to know our phase changes. Where'd my pen go? Oh, there it is. I found it, guys. Don't worry. Don't worry, guys. Oh, what happened? Strange. There we go. Alright, so we have 3 phases. And if we imagine them being stacked up vertically in increasing energy, we'd have to put solid at the bottom. Alright, so solid would have to be at the bottom. And then above that, liquid has slightly more energy. So liquid would go right above solid, and then above that would be gases. So gases have the most energy. So as you heat something up, the energy would go up, and you'd go solid to liquid to gas. Now you need to know what these look like. So if we do like a zoomed in to a solid, we'd have the particles next to each other, vibrating but not really moving. Random molecular motion is very low. Okay, and the intermolecular force is strong. I guess I should actually write that down for you guys. You may need some extra paper as we're taking notes. If you run out of room, just depends on how big you write. Feel free to pause it to grab some paper. Okay, so kinetic energy is low. Intermolecular force is high. Motion of particles is low. This kind of goes with kinetic energy. Let me move it around. That didn't move anything. Okay, there we go. It's moved around now. Alright, a liquid is going to move around a little bit more, but it's not going to fill its container. So I'm drawing little arrows because it's moving around a little bit. Some of you are much better artists than I am, but it's not filling the entire container. So I'll draw a little line showing that it's kind of like that. Well, let's finish the diagrams and then we'll finish the descriptions after that. Gases fill their entire container, so I'm drawing it pretty much everywhere, and they move a lot faster. Okay. So let's do these same three for these ones. So I'll have to change my answers. So for liquid, kinetic energy is kind of in the middle. Motion of particles is kind of in the middle. And intermolecular forces is kind of in the middle. Okay. Whereas a gas has a high kinetic energy, motion of particles is very high, and intermolecular force is very low. Because if they attracted each other more, they wouldn't move around as much. Alright, there's one more part to Unit 7A, which has to do with reaction energy diagrams. What is going on with me? Alright, so reaction energy diagrams. They show how the energy changes in a reaction. So they're pretty much always going to have axes for the y and the x that are going to, the y is going to be energy. Alright, so energy. Sometimes it'll say potential energy, but it's the energy. And then the x is going to be the reaction progress or reaction coordinate or time, because as time goes on, the reaction's going to go on, right? And generally, we'll just be doing sketches, but you could see more detailed ones that actually give you the energy values. So you're going to start at the energy of the reactants. The energy is going to increase until it gets to the transition state. So this is the transition state. And then the energy is going to decrease until it gets to the energy of the products. And here I've drawn the products lower than the reactants. This would be exothermic. If these products ended up higher, it would be endothermic because it's going up in energy. All right. The activation energy is how much energy it takes to get to the transition state from where you start. So it would be this distance right here, basically. So like if you started at 5 kilojoules and the transition state was at 15, then this would be 10, just for example. The heat of reaction is the distance from the reactants, which that's where the reactants start, to the products. Okay, and so if the products, if this was at 2, then this would be 3 kilojoules, right? Except the delta H, the actual heat of reaction, would be negative 3 kilojoules because it's going down, which makes sense because it's exothermic. All right. So I guess I need to label these. This one right here is the activation energy, and this vertical distance here is the heat of reaction. All right, feel free to pause and catch up or replay any of that. I'm going to move on to Unit 7B. All right. So here we're going to deal with specific heat capacity, latent heat, and heating curves. So we'll just start off with heating curves. So let's get some axes here. Oh, that looks a little crooked. Whatevs. So it's going to have temperature on the y-axis, and it's going to have heat added, or time, assuming constant heat being added, on the x-axis. So if you start at a solid, which they typically would, so solid, you're going to first increase in temperature until you hit the melting point. Then it's going to start to melt, which means all the energy being added is a latent heat, which is just melting it. Eventually it's going to melt all the way, so here this is melting. And it's going to start increasing in temperature again until it hits the boiling point. So that's boiling point, BP. And then it's going to start boiling. Now it takes longer to boil than it does to melt because boiling takes more energy. So this is vaporization, just to use more vocabulary for you. And after it's fully vaporized, it'll continue to heat up if you continue to add heat. Okay, so it's a solid right here. I'm just going to switch to using letters. This would be a solid and a liquid. This would be just a liquid. Here it's vaporizing, so we have liquid and a gas in the same container. And then here it would be just a gas. Okay, so make sure you know where the phase changes are happening and what phases are present along each section of the heating curve. All right. We've got our two equations for latent heat. We use Q equals m times delta H, either fusion or vaporization, depending on which section you're on here, melting or vaporization. And then we have the specific heat capacity, which is Q equals mCp delta T. All right. I'm just going to color code this actually. Let me change it to, let's do purple. Oh, missed some. All right. And then here, the specific heat capacity you're going to use when it's just one phase increasing in temperature. So right here, or right here. Now these are all going to have different CPs. The latent heat you're going to use when it's changing phase but not temperature. So right here or right here. And these are going to have different delta H's, but it's the same equation. Okay, so different CPs for purple, different delta H's for red, but the same general equation. So let's just see if we can do at least one example before we run out here. I don't want this video to be longer than 15 minutes. Okay, so let's say you heat up 10 grams of water by 30 degrees Celsius from 20 degrees Celsius to 50 degrees Celsius. How much heat is required? How much heat is required? What, the same thing, right? So first thing we want to do is we want to annotate this. So it's asking how much heat is needed, so that's Q. It's giving us 10 grams, which is mass. It says by 30 degrees C, so that's delta T. It says from 20, so that's Ti, and 50 is Tf. So this is a change in temperature, so we're going to use Q equals mCp delta T. All right. We don't have Cp, at least given here, but we do know that from our equation sheet, Cp is actually the specific heat of water. It gives it to us right here, 4.18 joules per gram Celsius. So let me just write that down somewhere. Cp equals 4.18 joules per gram degrees C. And now I can plug in for Q. So Q equals 10 grams times 4.18 joules per gram degrees C times 30 degrees C for my delta T. Grams cancels right there, degrees C cancels, leaving me with joules. Okay. So we just punch this in here. 10 times 4.18 times 30 gives me 1,245. 1,245 joules. Now, standard C is just doing simple conversions. So if I wanted to convert this to kilojoules, that's an example of the type of simple conversion you'd do. So you'd put kilojoules on top, joules on the bottom. We know 1 kilojoule, kilo means 1,000, is 1,000 joules, so joules cancels, and we get 1.254 kilojoules. All right. If you're nervous about standard C, I advise you to set up a meeting with a tutor or come to office hours. But it's really not too bad. It's just a lot of common sense, totals, things like that. All right, but if you are nervous, come on in. Okay? Work hard, make sure that you learn the material. You're going to do great. I believe in you all. Bye-bye.